In this session we're going to look at sampling. Now, sampling is based on the selection of representative items from the population. The idea with sampling, in a nutshell, is to reduce costs. We sometimes can't examine the whole population. It's too expensive. It's too time consuming. So instead of doing that, we take a sample. And based on the calculations from the sample, we make estimates of what the values would be for the population. So we have a population and we draw the sample of the population. We select a sample out of the population, we calculate, let's say, the average for the sample, and then we use that to estimate the average for the population. It's much cheaper to take a sample, as I said, than to look at the whole population. So that's one of the reasons why we sample. If we test the whole population, that's known as a census. So a census is when we look at the whole population, the population of cars in the country, or the population of carrots grown by farmers, or the population of school children, or the population of whatever it is we're looking at. So if we take the whole population, it's the census. It's a census of that particular attribute we're interested in, or that particular variable we're interested in. Now there are two objectives to sampling. One is to describe the population. This is known as descriptive statistics. For example, determining the average miles driven by private motorists per year. Now that would be describing part of the population, describing something about the population. So it's a descriptive statistic. Secondly, we use it to make inferences about some aspect of the population. This is about testing an idea or a hypothesis. For example, how sensitive are customers to price changes in a certain supermarket? So there may be a certain hypothesis based on some piece of theory or some conjecture of some person. They have a hypothesis that states that if prices increase, then customers visiting this particular supermarket will stop going there. That's the hypothesis. And statistics could be used to test that. These are inferential statistics. Now, when we look at sampling, we're basing it, as I said, on the population. And to do that, we use the normal distribution, as it's called. Now, this will be the subject of other videos, and I'm not going to get into it in detail here. But it's important that we know that the type of distribution that we're sampling from. And the normal distribution is one that occurs in nature. It's a very powerful discovery within the social sciences, and it's used widely in business. Putting it quite simply, if this was a distribution of, let's say, the heights of schoolboys aged 14 in the country, what we would find is, I'll put the cursor onto the screen, what we'd find is the majority of boys are a certain height. So the majority here, this would be the frequency on the vertical axis, the majority are this particular height here, whatever it is. It wouldn't be a 0 because we have manipulated the axis here. But let's say it was whatever. So the majority would be there. Then we'd have some boys who are very tall for their age over here. There'd be a lot fewer of them, but they would be very tall for their age. And some boys who would be quite short for their age. So what we have is this distribution, which is known as the normal distribution, and it happens a lot in nature. It could be anything. It could be the weight of cattle of a certain age in a certain part of the country, or the size of carrots grown by farmers in a particular part of the country. It varies. It's so wide-ranging. It happens in so many areas of our life that we're not even familiar with. We talk about it, oddly enough, as if we know. For example, in general conversation, we say somebody is tall for his age. Well, tall compared to the average, I presume. So if we said the boy was tall for his age, he might be over here, tall compared to the average. The average, the majority here, the frequency here is the majority are of this height. This one is over here. So this is a very, very powerful curve. It's a very powerful piece of thinking, a powerful discovery about the way nature seems to organize itself. If we calculated one standard deviation either side of the mean, that would be 62% of the population. Now we'll deal with standard deviations also in other videos, but for the moment, if we took one standard deviation, so we move from, let's say, the mean here, this is the average, we'll call it 0, and we moved across one standard deviation and one standard deviation on the other side, we would have 19.1 plus 19.1, which is 38.2, plus 15 plus 15, which is plus 30. So 38.2 plus 30 is 68.2. In other words, 68.2% of, let's say, the boys are within that height range, are scattered around the average that much. So 62% are in there. It's quite a powerful statement. If we had two standard deviations, going over to 2, this is 2 here and 2 over here. If we took 2, we'd have 95.4% fall within this range. There will still be some falling outside of it. Up here, some extremely tall boys and some very, very short boys over here. So again, two standard deviations either side will give us 95.4%. There are different ways of remembering it. I tend to remember it as 1.96 standard deviations is 95%, and 2.54 is 99%. But that's just the way I remember it. It's worth knowing that particular little fact, because one standard deviation either side is 68.2% of the population. This is important. We'll come back to it later, and it will be the subject of other videos. Now let's go back to sampling issues. Well, first of all, the sample must be representative. A sample must represent the population and reduce bias. If we were doing an investigation into retired people, some aspect of, let's say, their expenditure, then the relevant population must be made up from retired people. That's the most efficient way of doing it. And also the sample must be selected in a way that gets rid of any bias. It shouldn't be based on friends or acquaintances or people in the local area. It should be selected scientifically. It should be what we call a random sample. A random sample means that every item that's selected has an equal probability of being selected. So every item selected has an equal probability of being selected as the next one. That's important. If that's not the case, then the sample will be biased. And the sample should be large enough to reduce sampling error. It should be sufficiently big. The sample size should be large enough to reduce any errors. You can't just ask perhaps one or two people and than make some big statement about the whole population. If the whole population was 1 million, so that wouldn't be very precise. So it needs to be a significant size sample. And errors must be explicitly recognized. For example, the average of a sample may vary from the average of the population. Now if that's known to be the case, then there should be some account of why that is the case. Why did that happen? If for some reason the average of the population was known and a sample was selected and the average was different, why is it different? So errors must be admitted openly. Let's talk about sampling errors. Well, first of all, set clear objectives for the sample. Be very clear about what the sample is attempting to do. Determine the budget, because that will determine the size of the sample, the technique to be used, and so on. I mean, how efficient the whole process will be, how the people were selected, and how the data was analyzed. So having a sufficient budget is important. Identify the precise sampling frame and population. Who is to be sampled? And try to work out where these people or these things, if they're inanimate objects, if they're products in a shop, where these things or these items can be found, where the people can be found or where the items can be found. Where is the sampling frame? Where can it be found? Then decide on the methodology. How is this going to be done? How is the sample going to be selected? Well, as I said, the best way of doing it is by picking out randomly the people or the objects. If they're picked out randomly, it gets rid of bias. But picking randomly is very complicated and also very costly. And as I said, it will be dealt with in another video, a separate video. Let's look at the whole idea behind sampling. Let's just have a talk about the whole idea behind sampling. Let's say we have a population here. We have lots of X's in here, red X's and black X's. And let's just say there are 40. I don't know how many are in here actually, but let's say there are 40. The population is equal to 40. There are 40 X's, let's say, in here. Don't count them because I haven't counted them myself. Anyway, let's say we have 40 in here. So we have a population of 40 X's. And we have 25 black and 15 red. So the proportion of red is 15 over 40. There's 40 balls in there, or 40 X's, let's say. And 15 out of 40 is 37.5%. So 37.5% of these are red. Now let's say we want to determine that with a sample. So we select the sample up here. And we should select the sample randomly, as I said. This is a sample in which every element in the population has equal chance of being selected. It's selected purely by chance, with no predictability. So now, we've selected randomly. One way of explaining this, let's say these are red balls and black balls in a bag. And you can't see into the bag. There are just red balls and black balls, and all of them are the same size and the same texture. Now if you draw out, say 10 of them, because you can't tell which by putting your hand into the bag, you can't see, you could draw out 10 randomly. That would be a random sample. Now let's see how it would work. Well, let's say we took out a sample and we picked out 6 red and 14 black. So we've picked out, let's say, 20. 6 and 14. 14 black, 6 red. So 6 red over 20, it's 30% of them are red. Now please note here, we know the true value because this is like an experiment. We know it's 37.5. We've calculated it to be 30. So that's our estimate. You can see it's wrong, but it's at the same time 37.5 and 30. It's not too far wrong, but it is wrong, but it's getting there perhaps. Let's put it into a table and look at it. So here we have sample 1, 6 and 14, and it's 30. Let's do it again. This time we draw out 11 balls and we look ahead, and we could have 11 and 9, which is 55. We have a second sample here, this one here, let's say. We have 3 and 17, so we have 15% are red here. 30% are red on the first one, 15 on the second one, and on this one, what I mentioned earlier, it's 55%. Well, we know the true one is 37.5. So some of them are pretty far off. This one's 15, that's a long way off. This one here is 55, that's quite a bit off as well. If we carry on doing that, carry on drawing out samples, let's say we take 7 samples, we might find those are the percentages. So what we really needed was 25 black and 15 red. Well, we've drawn out 20 on each of them. We should get the proportions here, but we're not getting anything like 37.5. If we take the average, we find it's 36.4. Well, 36.4, that's very close to 37.5. So by drawing out the samples and taking the average of the samples, we have got very close to the population. So we haven't actually worked out, let's say, the average for the population. We could have worked it out by picking out the samples and taking the average of the samples. And that's pretty clever. Let's talk about sampling errors. Well, we have something called the standard error. And the standard error is it's the standard deviation of the sample divided by the square root of the sample size. That's just a little formula that gives us what's called a standard error. So the S is the standard deviation of the sample. Now, if we take the standard error and multiply it by 1.96, what we get is, if we have an estimate of the mean and we add 1.96 times the standard error and subtract 1.96 times the standard error, we would have 95% confidence in the true value falling in that range. If you remember back here, I said 1.96, 95%. So if we go 1.96 standard deviations across and minus 1.96 standard deviations across, we get 95% in there. So we can see how the use of the normal distribution helps to explain this one. So what we've got now is a way of estimating the population mean. If you go back to, let's say, a sample here, we'll take this idea of using a sample. Let's say we have a sample here of prices, and we go back to using this sort of table format. Then we have a number of prices down here. We've got an average price, £5.80 9, and a standard deviation of 83 pence. Right. Now, the standard error here is the standard deviation of the sample, which is 0.83. The sample size is 7, so it's the square root of 7, so that becomes 0.313. So the standard error is 0.313. Now, 95% confidence interval is 1.96. Therefore, the confidence interval, CI, the confidence interval, is plus or minus 1.96 times 0.3. Well, 0.313, which is plus or minus 0.614. So the population average should be between the average of the sample, £5.89, plus or minus 61 pence, 0.61 pounds. In other words, the population average should be between £6.50 and £5.28, 6.5 and 5.28. And we're 95% confident that that is true. We're not 100% confident, because it is a sample, but we're 95% confident that that is true. And it's based on that simple calculation. So if we know the average of the sample, and we know the standard deviation of the sample, we take the standard deviation divided by the square root of the sample size, which gives us the standard error. We then multiply that and subtract, add it and subtract when we multiply it by the standard error. So we get 1.96 times that, which is equal to plus or minus 0.614. We add and subtract the 0.614 to the average, giving us this. And we're 95% confident that that is true. So we can see the power of sampling. So when we use sample information, we always quote the average with its standard error. Now you can actually use this formula and transform it. For example, if let's say we wanted to calculate the sample size. Now to calculate the sample size, we've got, that's our formula, the standard error is equal to the standard deviation of the sample divided by the square root of the sample size. Well, if we just manipulate this, we just multiply across by the square root of the sample size and divide by the standard error, we'd get that, and if we squared it, we get the sample size. So if we now put in the figures we had, we know what the standard error is 0.31, and we know the sample size, the standard deviation of the sample, 0.83, and we square that fraction, then we get 7.1 or 7. We had 7 in the sample, so it's not surprising. So there is a way of working out the sample size from the formula as well. So you can see from these simple calculations the power of sampling. But it is based on probability. It's based on the idea of 95% confident or 99% confident or 68% confident or whatever confidence interval we select. But we're not 100%. We could be wrong still. And it's important to bear that in mind. Now let's look at the types of sample. Well, we have non-random samples. The results may not be very reliable and they may suffer from bias. So non-random samples, well, Convenience sampling is an example of this. Opportunity sampling, it's sometimes called. These are very unreliable and very biased. Convenience is pick a sample, okay, I'll ask my neighbours, and I'll ask the lady in the shop down the road, and I'll ask some of my friends. That's convenience, but that's very biased. That's not the way it should be done, and that does not lead to an accurate statistic. And applying the formula to that simply does not make sense. The data in the sample must be selected randomly. It must be selected in a way which is more objective than this. We also have what's known as snowball sampling. Simply ask recommendations and extend the sample that way. It also suffers from bias. So snowball sampling could be, I'll ask my friend, and then I ask my friend if he or she has got some friends, and would they be willing to help me? And if yes, then I go and ask them. Then I ask them, have they got some friends, and could they help me? And so on and so on. So it's like a snowball getting bigger in the snow as you roll it. So I've moved away from my initial friend to his or her friends, and then on to their friends, and on to their friends again. But it's still biased. It is still not very scientific. Random sampling is about the only way to do this, but it's expensive and it's difficult to do. Each item in the population for random sampling has an equal chance of being selected. But the selection may be difficult. It may be possible to number each item in the population and then select using random number tables, or even have a draw, put the numbers into a drum or into a hat and pull out a number. That might be possible. But there are things called random number tables, which you should try and look up on the web. Just get an example of what they are, and just have a look at some of them. But essentially, it's difficult to find random numbers. That's the point. If the population is large, selection may be extremely difficult, and the sample may be unrepresentative. So large populations create big problems. It's very costly to select the items randomly. Two alternatives are sought to reduce this expense. So the alternatives might be sampling, and the sampling could be perhaps quite a small sample but done properly, or perhaps a range of small samples but each of them done properly, rather than taking on a large sample which is expensive and perhaps very difficult to do because you're looking for random numbers. There's also something called stratified sampling, to focus on categories within the population. These are called strata. Then random select or random sample within the strata. So for example, if you are looking at university students, then university students are a subset of the whole population of people. But why sample from the whole population of people? That would be inefficient. Try to sample from university students only if these are the people you're interested in. If you sample from the whole population, it's inefficient. Some of the responses will not be applicable, will not be usable. So for example, student attitude towards banking services. Select the student strata and then random sample within that. And that's the essence of stratified sampling. There may also be substrata. For example, female students in Scotland. their attitudes towards banking services. So when you select student strata, you have to realize that there are substrata in there. That might be important or it may not be important. It depends on what you're trying to discover. But you have to realize that there are subsamples. And the example I've given is, for example, female students in Scotland. That might be a substrata. Quota sampling. Well, this involves deciding the size of the sample and its characteristics. For example, if 52% of the students at a given university are female, then a survey of student attitudes regarding some issue should have 52% of the sample drawn from the total population should be female. So if 52% of the students are female, then 52% of the sample should be female, ideally. So that's quota sampling. So quota sampling reflects the population structure. Now, in this video, what have we done? Well, we've looked at sampling, we've looked at the idea of sampling, we've looked at how sampling can give an indication as to the characteristics of the population. We've looked at the confidence intervals and how the standard error is used to generate the confidence interval using the normal distribution. We've talked about different types of sampling, the various types that we've just gone across, and each of these are important. So it's important, this is quite a detailed class. It's important now you go back over the class, stop the video from time to time, make your own notes, and examine the ideas in more detail. Perhaps go online and seek further clarification. There's lots of material online about sampling and about this type of work. Try to avoid the deeper mathematics, because what we need here is a good understanding of what is going on, not necessarily the intricate mathematics that lies behind it. In the meantime, that's all we need to say for the moment, so thank you for watching.